Just as we have derivatives of trigonometric functions, well, we also have derivatives of the inverse trig functions. First, a general reminder, what is the inverse trig function? Well, I'm not going to talk about all of them, but I will tie in sine of x and arc sine of x. So this is the sine of x curve. It's not what we're normally looking at. We're normally looking at 0 to 2 pi, which means right here is 1 pi. It would continue again like this. I'm focusing more on, we went from negative pi to pi. All right, so we do go this way and we're going this way. I think everyone can follow along. If I had a y equals x line here, okay, and if I were to take the inverse, well, the inverse is a reflection over that. What happens is you start getting something that looks like this. That's not enough different color. There we go. All right, so it's going to do this, and then it's going to do this. All right, and basically what you end up with is this. I have a better picture of it. This is the pink diagram I just drew. This is in magenta, I guess. So how do I know that that's this inverse? Well, graphically I just showed you, but here, let's do it mathematically now. So if you're starting off with y equals sine of x, and the way you take the inverse is you switch the x and the y. Graphically, it's a reflection about the y equals x line, and algebraically, we switch the x and the y values. Now we need to get y equals in terms of x. So what you would do is you take the arc sine of both sides, and this may ring a bell. I guess I don't need a parenthesis right there for the x. So now we have y equals arc sine of x. Arc sine of x is also written like this. Be familiar with both ways, just simply because you'll see them written both ways. All right, well, so now back to this graph. So the sine of x graph, what I did was I cut it off here at pi over 2, and then I cut it off here at negative pi over 2 because that would guarantee a function when I take the inverse of it. So now here's your pi over 2, right, and here's your negative pi over 2. And the reason why you see the x and the y axes switch is because, well, they do on regular functions too. It's just that normally they're all in 1s, 2s, and 3s. Here you see that 1 is in radians, so the y becomes the radians. And now you can also see that it would also pass the vertical line test, because never once would it do something like this and arc back where it wouldn't pass the vertical line test. While this is not directly necessary for the homework, it is good to kind of have a visual of what we're talking about before we start working with these functions. And this also, I'm going to, leave this if you want to pause and kind of look at these domains and ranges for the different arcsine, arccosine, arctang, and the other three. Well, please do so. Again, this is just to get a visual so we know what type of functions we're working with here. What I'll do for those interested in getting this in your notes so you see the domains and ranges, I'll make this larger for you. Okay. All right, there you have it. So pause if you need to. I'm going to move on. Here, my friends, are the derivatives for the 6 inverse trig functions. Normally, the way I usually write these, I usually kind of do this. I do sine. Well, here I'm going to do u. Sine of u, cosine of u, tangent of u. And then if that's how I write it, I would then usually write the cosecant of u over here, and then the secant, cosine goes with secant, and then tan and cotan. There's other relationships between these functions, and what the book is doing here is they're just tying in the sine and its co, the tan and its co, and the secant and its co-secant. Regardless, whatever you feel more comfortable with, you can write it in this order or this order, as long as you know which one is which. I am going to focus on the arc sine, since that's what I just kind of started focusing on the first slide there. Let's start off simple when our u is simply just an x value. So what if I gave you y equals arc sine? Again, it can be written like this or like this, so be comfortable with both notations. I'm just going to start with the arc sine of x. So let u be x, if you will. Well, when it says to take the derivative of the u value right here, right, because it's going to say u and then take the derivative of u, well, the derivative of x is just 1, so that ends up being a 1 there. Let's get back to our example here. So the derivative of y with respect to x, here's your derivative. And if I follow this notation, it says, well, the way I memorized it, it's 1 over 1 minus u squared times the derivative of u. That's just how I have it memorized in my head. But again, what happens is when you multiply them, well, you see that you get what is written up there under Theorem 516. Since our u is an x value, what we have is we have the 1 over the square root of 1 minus x squared times the derivative of x. Remember, this was our u value, so that is just the 1, right? 1 over 1. So what you're left with when it's just an x is this. All right, that's the easiest one. And now I want to show you just one proof. I'm not going to go through 6 proofs here, but I'm going to show you one simple proof to show you why the arc sine, why the derivative actually equals that. Let's give ourselves some room to work with here. I'll get rid of these items, and I will leave, let me make those smaller. And this right here is what we're going to prove, so I'll leave that right there. Let me do that again. There, okay. That's what I want to do. I will rewrite our y equals arc sine of x right here. And we should know at this point that that is equivalent to this. Remember, if I gave you this and you took the arc sine of both sides, what would happen is you'd have y by itself and you'd have the arc sine of x. So mathematically, these two equations are the same. Now what I want to do is I want to take the derivative of both sides with respect to x. So I'm going to take the derivative of this side with respect to x, and I'm going to do the same thing over here, the derivative of this side with respect to x. On the left, what happens is, well, the derivative of sine is cosine of y, and, well, since it's with respect to x, we then take the derivative of y, which is dy dx. All right. And then over here on the right side, well, with respect to x, x becomes 1. And when you solve for dy dx, you get 1 over the cosine of y, which is not, it's pretty neat looking. The only problem is I did mention we want to have this in terms of x. Right now our derivative is in terms of y. We need to change that. Do you remember the Pythagorean identity? Sine squared x plus cosine squared x equals 1. Regardless of what our variable is there, this still holds true. So even if we had this or a theta or whatever variable you want, it still holds true. Now, we have a cosine of y down here. We were trying to get rid of that. We want to substitute. So why don't we try to get cosine of y by itself? And if we do a little algebra here and move that over, we get that. And then I get y. I misspoke. We need to take the square root before we get y. So if I take the square root of both sides, well, remember the reason I did that was we had a cosine squared right there. So when you square the square root, when you square root to square, you get that by itself. And the sine squared y, well, that can also be written like that. And, well, why did I write it like that? Well, check this out. Cosine of y equals, here's 1 minus the sine of y squared. Well, what's the sine of y? We actually know that over here. Remember what that said first. It said x equals sine of y. All right, well, I could either call it sine of y or I can call it x. And since we want it in terms of x, why don't we call sine of y x? And a little hocus pocus abracadabra, I'm going to substitute in for the cosine of y and call it the square root of 1 minus x squared. And there, my friends, is your proof. Oh, but there's someone saying, what about that plus or minus out there? I forgot to address that. Well, notice how I didn't write plus or minus and I left it plus. Well, here's why I did that. ASTC. You've seen that before. And, well, the cosine function is positive in the first and the fourth quadrants. And since the domain that we're working in is between pi and, well, you can call this 3 pi over 2, or it's also negative pi over 2, right? If you go this direction, it's negative pi over 2. Well, since that's the domain we're working in, well, cosine is positive. Now for a few examples. What if we start off with arc sine of 2x? So u is our 2x. If it helps you, maybe identify it. Now you are going to take the derivative of the arcsine of 2x with respect to x. So that gives us 1 over the square root of 1 minus our u squared. Well, remember what we said u was. U is 2x. And then you multiply it by the derivative of u. Well, u prime would be 2, so you multiply it by 2. And your final answer here is going to be a 2 times 1 in the numerator. And, well, anything times 1 is itself, but we can clean up this right here. Don't forget, you have 2 of them. That's 2x times 2x. That is 4x squared. That would be the arcsine of 2x. Well, how about another example? While I'm not a big fan of just telling you to straight up memorize something, I do understand that, deriving these each time the way I did the first time is really not practical. So get familiar with these derivative rules up here in the corner. Let's do another one. I give you the arctan of 3x. And again, that could be written just as a reminder as arctan 3x. All right, same thing. Now we're going to take the derivative of this function with respect to x. We want it in terms of x's. And that's going to look like this. Well, the arctan is going to be 1 over 1 plus our u value squared. And our u value in this case is 3x. And then again, it's times the derivative of that, which would be 3. Right? If it helps, well, write it. U was 3x, and then the u prime we needed was 3. When you combine those two, you get 3 times 1. You get 1 plus. We could do the same thing here. Remember, the rule is you square both of these factors, so you get 9 squared. 9x squared. So the answer here is 3 over 1 plus 9x squared. Let's do one now where u has a radical in it. Now let's just call it square root of x. Let's start simple. And let's change the color up. How about a little of that? What if we give you the arcsine of the square root of x, radical x? And I want you to do the same thing. We're going to take the derivative of this with respect to x. And let's do it. First thing, I hope most of you are in that habit by now. I'm going to do that because it's easier to take the derivative. And let's see, the arcsine. Well, that means it's going to be 1 over the square root of 1 minus u squared. In this case, our u value is the square root of x. And then times the derivative. Well, again, if u is x to the 1/2, well then u prime is going to be 1/2 x. And then you reduce the exponent by 1. So let's do that. That's going to be 1/2 x raised to the, there you go. What does that come out to be? Well, this is all one term here, right? Just a bunch of things being multiplied together. So let's do one thing at a time. This one right here, we have 1 in the numerator, and then in the denominator here, this is going to be the square root of 1 minus, well, the square root of x squared is just x, right? And then the next factor right here, the next thing being multiplied is, well, we have a 1 in the numerator, so times 1 if you want, and then we have a 2 downstairs we have to multiply. And this next term right here, well, that's x to the negative 1/2. That goes downstairs, and yes, it's in the square root. Let's clean this up a little bit. We have 1 over, well, yeah, I'm going to keep the 2 on the outside, but notice this. These two are square roots. We are allowed to multiply the underneath values. That's the same thing as this. X times 1 minus x. And I'm going to just clean that up by saying we have 1 over 2, and the square root would be x minus x squared. How about one more for good measure? All right, let's kind of put this stuff over here. What if we're given the arc secant of e raised to the 2x? All right, it's getting interesting now. We're going to follow the same pattern. We're going to take the derivative of this, and we're going to do it with respect to x. And the arc secant, well, let's just so our eyes can focus on what this formula is here. It may very well help to identify what that e is. I'm going to write this right down here. U equals e raised to the 2x. So we'll get back to that in a moment. But let's take the derivative here. So I have 1 over the absolute value of u, well, u was e, I need a little more room there. It was e raised to the 2x. And then it's times the square root of our u value squared minus 1. Our u value is e, whoops, that's pretty sloppy, e raised to the 2x. And we multiply that by u prime. Well, what's u prime? U prime, we leave what we see, and we multiply it by the derivative of the exponent. So the derivative of u prime, is 2 times e raised to the 2x. So we're going to multiply it by 2 times e raised to the 2x. And if you want to put that over 1, that'll help us clean it up here. And our final answer in white here, well, when you multiply these numerator values, 1 times anything is itself, so we get this. And downstairs, well, again, 1 times anything is itself, so we have this. We can clean this thing up. Do you remember your exponent rules? You multiply in this situation, so that's going to be e raised to the 4x, and that is minus 1, all under the radical. Now we can clean this up even further. This right here, we've mentioned this, Mrs. Babcock mentioned this in the first video, how the exponential function, it's always this, right? It's always positive, okay? It's always so that absolute value in this case is really unnecessary because it's always going to be positive no matter what x value you plug in, as you can see. So with that said, if you rewrite that without the absolute value, since it's kind of optional, not kind of, it's optional, this is what you have. And I think you see where I'm going with this. That allows us to cancel these two things out, and our final reduced answer here would be 2 over this. There you have it. This one right here looks more intimidating than it really is. So what you just need to remember is whenever you have a sine, cosine, or a tan function, you have an angle value, right? In this case, well, instead of calling it that ugly arc cotangent of t, what if you were to call it u? You've noticed that they've been using u as a substituting variable. Well, if I call u arc cotangent of t, well, then that should make sense, right? All I did was substitute in. So consider this. If this was your y function, right, and then you go ahead and you take the derivative of this, which is y prime, or dy dx, then you're going to get this. You're going to get secant squared, you leave the u, but then you need to remember to multiply that by the derivative of u. With that in mind, let's get back down here and start with the derivative of y in terms of t. So that would be, well, we have a tangent of an angle value, so that would be, that's tangent of u, and that would become secant squared, we leave the angle value, in this case it's arc cotangent of of t. But then, like we said up here, we now need to multiply the derivative of that u value, which in this is representing u prime. We're going to get that derivative up here under the arc cotangent. So we want, and again, this is just how I write it, it's mathematically equivalent. I have negative 1 over 1 plus the u value squared. In this case, our u value is just a t, and we square it. And the derivative of t is just 1, that's why we don't need to put that part. All right, well, let's come clean this up if we can. Well, this is really all just over 1. Remember, this arc cotangent, this is the angle value with the secant squared theta, so that stays with that. So we have a secant squared of what? Secant squared of arc cotangent t. That's the angle value. Oops. Times the negative 1. I'm going to put that negative right there in front. And the denominators, well, the denominators are just 1 times that. So it's really just 1 plus t squared. And that right there is our answer. Now that we've taken the derivative of a few of these inverse trig functions, let's go ahead and find the entire equation of the tangent line to the graph at a certain point. So here's our coordinate, and here's our function. So I was about to say xy, but we have a t here, so it's a t and a y of t. Well, the derivative, let's start with that, because that's how we're going to find the slope of the tangent line. I am going to go y prime of t. Now, arc secant, well, I have it identified here. Arc secant is 1 over the absolute value of u. Remember what the u value is. In this case our u value is 4t. So I put 4t here. And then I have the square root of u squared minus 1. In this case, my u is 4t. Then we multiply it by the derivative of u, which is 4. Right? If that's u, then u prime up here becomes 4. And that's what it says, multiply by u prime. And then you put that in the numerator. You could do it all at once like the notation says up here, but I'm just, in my head, I have 1 over that times the derivative, so I'm going to write it like that. It's mathematically equivalent. Up here, what can we do? That's 16t squared minus 1. And, well, what can we do here? Think about this over here in white. I guess I can call it a t instead. Let me, well, we'll just call it an x. Doesn't matter. Whether I call it this or this, that's never, ever, 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 ever going to make a difference, because whatever you plug in here, you're going to make positive and then multiply it by 4. Whatever you do here, well, what if you multiply it by 4 first and then make it positive? It makes no difference. So the 4 is a positive. We know the absolute value of 4 is positive 4. So what we can do is this. The only thing we have to be concerned about is the thing that's changing. Sometimes if it's a negative, we need to be mindful of that. But the 4, that does not impact the absolute value piece of it. And here we have this. And that's just going to make our numbers a little bit smaller and a little bit easier to work with. I could put a 1 over there. So now we have this. We have the derivative in terms of t is 1 over the absolute value of t times this. T squared minus 1. And now why don't we go ahead and at least find the slope of the tangent line at this time. So again, this is your t, and this would be your y of t in the ordered pair. So we have radical 2 over 4. I'm going to plug that in where I see a t. All right, so that's going to be the absolute value of this. And then I have this, and that's squared. In there we have radical 2 over 4. Sorry for being tight. I think we could read that. And there's my minus 1. Let's move this up so we have some room. All right, well, we got some fractions. Let's take care of what we can here first. So the absolute value here, well, the absolute value of radical 2 over 4 is radical 2 over 4. And then in here, that was easier than you thought, right? Well, what do we have? We have 16. Now we have to square. So radical 2 times radical 2 is 2, and 4 times 4 is 16. Don't forget how to square fractions like that. And there's a minus 1, and there's our numerator up there, 1. Let's just clean this up a little bit. We have radical 2 over 4. I'll take care of those denominators in a minute. Inside here, well, those 16s are going to cancel, and, well, you're left with 2 minus 1. And 2 minus 1 is 1, and the square root of 1 is 1, and right there, well, I'm going to call that 1. And now we have this. We have radical 2 over 4, and I like to just multiply by the common denominator. So I'm going to do that, and that gets rid of that, and that gives you 4 times 1, and that gives you a radical 2 times 1. And you don't have to rationalize your denominator. That's the slope of the tangent line. If you really want to rationalize it, this is how you do it. You just multiply the top and bottom by whatever radical you have, and that's going to give you this. It's going to give you 4 radical 2 over 2, which reduces to 2 radical 2. All right, so I guess we could use this one. It looks nicer. Onward, we are almost done. Our goal was to find the equation of a tangent line. The equation of a tangent line is a straight linear function, and we can use the point-slope form of an equation to find it. Technically, since we are not really dealing with an x and a y, I guess I should call it t, and, well, we can call it y. It's y of t. So let's just call it this. It should be y minus y1 equals m, and this is just going to be t minus t1. T is our variable. Let's be accurate. Let's plug in our variables. Well, the slope of the tangent line, well, that's what we found over here in green. We know what that is. That's going to be 2 radical 2. And, well, let's do the t values first. So the t, here was the coordinate we had written up there. Let me copy it down in case you have it on a different page. It was this. All right, well, that means that I have t minus radical 2 over 4. And over here I have y minus pi over 4. Now, while that is sufficient, because right there, this is the point-slope form of the equation, that's if it just said find an equation. That is an equation. For those of you who just can't resist and want to put it in slope-intercept form, which again, if it just says find an equation, is certainly not necessary. Well, what would we do? We would do this. First, there is no parentheses, so we would distribute, and that would give me 2 radical 2 times t. Some people would prefer to write that like this, so you don't think the t is under the radical. So fine, I'll write it like that. And then here, well then if you distribute here, you're going to have negative, I have 2 radical 2 times radical 2 all over 1 times 4. There. Let's clean it up. I have y minus pi over 4. This is 2t radical 2. And what do we have here? Well, this right here equals 2. That equals 4. That's minus 4 over 4. Y equals 2t radical 2 minus 1 plus pi over 4. Right here, this is probably the best you can represent it, because even though you want it in mx plus b form, if you will, or mt plus b form, here's your b, and the reason why you can add numbers up, but this is an irrational and a rational, so that's probably the best you can do. So let's call it good at this point. I would like to finish this video off just pointing something out I think is quite useful. It's on page 378 in your textbook, so if you even want to just go there and review it or copy it or do whatever works for you, even if you want to just pause the video and do whatever you want with it here, I just want to point it out. It's a nice little wrap-up, a summary of everything we've done so far, all the different derivatives of what we take. There might have been 1 or 2 in here we didn't address, maybe not, but anyway, they're all pretty useful. Here's the quotient rule, the product rule, and if it helps, great. If not, well, good luck with the homework.